Hi, hello, and welcome to our exam review. So we are going to be studying together for our Chem 3A Introductory Chemistry exam. We will be focusing on Chapter 8 through 11. So the way that this exam review will work for you watching this video, is a recording of my review session that was held in the fall semester 2024. So what I recommend doing if you are here to watch the recording is the first part of it. You'll see below is I have the chapter labels for all the different things we will be covering. If you are here to learn exactly what's on the test, that'll be the first chapter portion of that review video. Afterwards, as you can see in the bio description below, I have a link to the Kahoot that this video is a part of. I entirely recommend you go along with the Kahoot and try to play along with it. So that way you can see what do you know, what do you not know. If you end up getting a question wrong, I have all the questions labeled in the chapters of the video, so you can fast forward directly to the question that you were interested in hearing about. If you want to watch the entire thing, that's fine too, but you can kind of skip around to which questions you need help with now. So I hope that this video helps. I hope the review helps. So this is the edited down version, and let me know if you need any help at all. So reach out to me, whether it's through email, Discord, or the comments below. And I hope that this helped. And let's learn and try to study and review together. All right, I will see you all during our review. Right, so if you go through modules, it'll lead you to the study module, which for this particular test, it's going to be on chapter 10, on chapter 8, chapter 9, and then chapter 11. So it's a decent chunk of material in this one compared to probably the other ones, but probably the good thing is that they're all related to each other, right? So what I would recommend doing first, right, on this test, as always, is take some time to yourself and go through the study guide. I mean, obviously, you're here, we'll go through it a little bit as well, but really taking that time for yourself and just kind of sitting down and absorbing, right? And not in the middle of the night to absorb all the information, but on your own. You can always go back to this recording and watch as many times as you want to help you kind of remember all the things. So the first thing is the test is going to be very similar to exam number 2. Being that exam number 2 went really well, it looked like for pretty much better than exam 1 did, at least in terms of score. So it looked like that was good. So last time, just to kind of refresher what happened, was it was roughly about the first half was pure multiple choice, and then the second half was multiple choice, but it had a component that allowed you to show your work, so that way you can kind of, I don't know. It served as two purposes. One, I graded on partial credit if you were on that right track. But two, it sort of like tricked you guys into being like, hey, show your work. So that way, hopefully, you will actually write your work, write your units, and you'd get the correct answer was kind of the hope. And I think it kind of worked because most people did get it correct. Compared to the multiple choice, actually, I think the percentage of like points without me giving partial credit was higher because people showed their work and actually kind of went through it. So if anything, it just benefits you to get that opportunity there. So these are all the math ones that will be on the very end of it. So when you're kind of going through these multiple choice, those last 15 are going to be the mathy ones, the balancing chemical reaction type problems, all that stuff like that. I tried to put the tests in order of chapter, give or take, so that way it's not like kind of shuffling and jumping around too much, at least like the best that you can, right? Stoichiometry, as you guys know, that's everything, so it's a little hard to do it for that one, but I attempted, right? Like that was kind of the idea, so that way your brain isn't. I would, as much as I would love it for you guys to be able to think like me, it's my brain is connecting to 4,000 different things at a given moment, so it's a little hard to do that. I don't need you guys to have your brain fried at all times as well. So it's a little hard to be able to think in that aspect. So what are you going to be able to get on this test? You do get an index card like last time, but if you didn't notice, and they already got screenshots from some of you of like, what? Like one side? You only get one side of an index card. So yes, this exam you only get one side. Now, why is it that I'm taking away a side? There's a reason behind this, and it's not to be mean. It's because on the final exam, I'm not allowed to give you an index card at all. So, and because it's a standardized final across all Chem 3A sections. So that one, I'm trying to kind of wean you off of it, is the thought. So it's gonna be really, you gotta kinda put what you think you really need on it, and probably, honestly, if most of you really think back to the last exam, you probably didn't use it all as much as you think you needed it for. It's more of like a it's more of as a comfort, like, it's like, yo, you got your card, it's really good, you have it there if you need it, but you might have looked up maybe a couple things, but you might not have needed it. There are a couple ways to be able to fit everything on that card. I don't say that you have to handwrite it. If you want to, you can type what is on that card. A lot of you did type it, and you could fit a crap ton of information on a typed card. I think the secret is about anywhere from 3 to 4 font size is the smallest you can go, depending on what you can see with your own eye. So you can shove a lot of material on that thing. So you are allowed to type it, but you have to be able to read it with your own eyes. You can't bring a magnifying glass or anything silly like that. You have to be able to read it, and it has to be 3 by 5 inches, just to specify that too. Um, and I noticed I didn't even put my units there. Oh God, look at me being terrible with units myself. So it's inches. Um, but you do get the yellow sheet on it. So, and I'll give you like the whole yellow sheet this time. I didn't really bother editing it down. The green sheet I'll give you, but I should edit that. It's only the solubility side. It's not the polyatomic part. So only the solubility part. I don't know why I wrote polyatomics on there. So it's that one side of it that has the solubility, the strong acids, strong bases, and the gas evolution reactions. So you have that side, and I put all that information on there. When it came to the polyatomics, I didn't put it on there because there's really no polyatomics on the tests that are like ones that I hope that you wouldn't recognize by this point, just because it's one of the ones that's, I don't know, based on how people are in class, like they just kind of know it because I've seen it 48,000 times by this point. Like I don't know which ones are on there, but like say if it's nitrate or carbonate or like sulfate or those more common ones that are like that. You see them a lot. What will I be able to give you on the standard exam? Oh, that's the next one. You're worrying too far in the future. Really, the only thing I can give you on that one is the periodic table, and then I can give you that comes with it, and then it's like a reference sheet that has like the constants on it, and then it has like a couple conversions on it. It's nothing like crazy, but there's really not a lot of formulas you need to know on it. It's kind of all things that I don't know. If you don't pass the final, if you want, I mean, no I'm kidding. Uh, Usually, if you're able to pass the regular exams, usually you pass the final. Most people do better on the final than they do on the regular exams. Um, at least what I've noticed. The past 2 semesters, people have been doing better on it. Most people will tell me the final is easier. The hardest part is the time component. So, but we'll talk about it when we get to it. So don't worry about that yet. There's no point in worrying about it yet. You can't. We got more to go. We'll review for that when we get closer. But no, you'll still pass the class even if you fail the final. The only reason you would fail the class is if you were at like, I don't know, you were already failing, or you were on like the cusp of failing, and that was what knocked you over. Yeah, one crisis at a time. Exactly. Let's focus on exam 3, not worry about the final and the lab practical and all that stuff. All that stuff first. All right. So you are allowed to get that index card. Bring pencil, your brain, bring your calculator. Make sure you bring a Scantron if you don't, so you don't forget that. So that way you have all those things. Now, some things that I made for you guys so that you have them. We have our study guide, right? So we'll kind of like look over it real quick so we can have it. You have a practice exam, which is it's one of my older tests. It's not really the more current one, but it's probably one of my first ones I gave when I started at FCC. And then We have flashcards if you want to review any terminology. Some students I know will print them out, use them. But really, the thing is practicing problems is the ultimate way to kind of be able to go through everything. Um, so if I were to kind of start here, let's bring up the study guide. So you can access the study guide from one of two places. You can either access it from the module, or you can get it directly on here, and it will give you what is going to be on it. Okay, so I got a question. Do I recommend doing extra time for DSPNS? If you have it, I would say it's never a bad thing to use it if you're okay with it. Just keep in mind that we have our team assessment afterwards, so you'll just have to schedule your exam at some time, probably outside of class time, most likely to fit it. But you can do. You're allowed to take it anytime within a few days of the actual test day. If that's what you want to do, if you have that, then yeah, use it. It's up to you. I won't be mad. I already submitted it to DSPNS for others, so it's up to you. Um, so looking at some things. So first thing, how would I study for this test if it was me and I was in your shoes? Um, there's all kinds of ways that you can really go through it. It kind of depends on how far back is your knowledge, I think, at the moment. If you have like a mountain of work to do still, that's when it kind of gets really tricky and hard, especially if you have a lot of videos to catch up on, a lot of homeworks and all that stuff. I would recommend getting as much done prior to probably a couple day window prior to the test as you can. So that way you can you need to be able to study on some things. So if you were all caught up, what I would do is first, I would probably, there's a couple different things I've done. Some things I've done in the past that have been really helpful is I will actually go back through my notes and I will actually rewrite all my notes in another notebook. So I did that a lot when I was a sophomore, junior, and senior in all of my upper division science courses. And it was a lot of work to do that, but it ended up forcing me to review through all the things and clarifying anything that didn't make sense in the moment when I was writing it down. Because pretty much I would do it alongside of any PowerPoints I had, or maybe I would have like the book open while doing it. So that way I can kind of like read through it and then I'd be practicing the examples like as I come across them in my notes. This was something that really helped me a lot when I was going through a class, is this where you're kind of rewriting them and then doing those examples again. Because you have the answers, right? And you can see like kind of um how did I think through them when I did it? Maybe you might be able to see that. And if you're stuck on something, you can message me and ask if you're like, oh, I saw this in my notes, but I don't see how you did this thing, or it doesn't match what I'm getting. Like maybe I made a mistake, which is definitely happens, in the videos or in class. I do it more than I care to admit. I wish I was perfect, but I'm not, right? Um, so you could do that. Afterwards, one thing that you could do is really is the key is practicing problems. Now the thing is there's a lot of problems that could exist across 4 chapters. Probably the most important chapters on this test, I would say they're the heavier topics. It's kind of hard to say. I would make sure you're okay with balancing chemical reactions, I think is because I try to pick things I think are the most important for what you guys would need for the next step when I'm making these tests. Meaning, like, I keep in mind for all the people that are in like the health science nursing majors, right? What do you need for physio? What do you need if you're taking Chem 1A the next semester? So I try to pick those particular topics when I'm making these tests. So, like balancing a chemical reaction. So, one of the things that you're going to see, like when you're doing those chemical reactions, is like, are you familiar with looking at, let's say, the different reaction types? Can you follow your recipes? If you don't know the recipes, well, there you go. That's something to write down on your card. So, probably while you're studying, one thing that I would recommend is if you want to early on, either if you do that notebook rewriting trick thing I talked about, or even if you're like, "Ah, I'm not gonna go do that. That's too much work." which is fair. I mean, it's not for everybody. You don't have to do exactly what I tell you. It's just whatever works for you. Make a card sooner, and what you can do is while you're studying, you can start practicing with it. And you might kind of realize that you don't need a lot of the information that's on it. And you'll kind of start to be like, cross it out, and then you'll remake the card. Or if you typed it, then you just like delete that line because it's just kind of taking up space. So you can kind of boil it down. So, balancing and going through and knowing how to predict the basic things. When it being that these are multiple choice though, so a lot of the questions I sort of purposely tailored them to give you like maybe like hints along the way, whether it's like to hint you to the correct answer, or it might give you hints for other questions, just to kind of so keep in mind that like sometimes I might have questions that are referring to topics on other questions that it might kind of reveal the not necessarily reveal the answer, but it might reveal the direction that's needed to do another question. So a lot of times I try to lead your guys' brains in the right directions while designing these things. Um, so make sure you're okay with balancing. That's where the end is. Now, with that, where does that kind of lead with what the next most important thing? It's probably a toss up between gas laws and stoichiometry. I think being that most of you have been voicing that you actually feel really good about gas laws, I put a little bit more gas laws on there. So chapter 8 is probably it might be the one with the most. It's either chemical reactions or gas laws. I'm not sure. It's probably a close tie. But I didn't go through and count them, but based on how many I kind of picked. With these ones, you need to make sure you're okay with the formulas. So write them down if you don't know them, right? You need the ideal gas law, you need the combined gas law, and then Dalton's law, right? Because when it comes to the combined gas law, you can make that into every other gas law, whether it's Boyle's, Avogadro's, Charles' law, Gay-Lussac's law. You can create it. Um, and that's all about like things changing, right? So how can one thing be able to move from state one to state two or initial to final, right? When you're kind of going through changing that. So make sure you're okay with doing those kinds of problems. And really probably the key is when I say by practicing it, is make sure you're okay with reading word problems and try to find new problems that you haven't done yet. You can practice the ones from class, that's great, but if you kind of see the answer, then you're already going to kind of know where to go. So try your best to pick new problems. So what I did is I recommended some from our online textbook. If you for some reason don't know we have an online textbook, just to kind of guide your eyes, right? It's right up here at the very, very top. We do have a textbook, so you can go to those particular questions. Every semester, I'll have somebody during finals week being like, "We don't have a textbook," and I'd be like, "What? We have one. It's just free, and you don't have to pay for it." That's the only reason why you might not see it. So, you can do those problems. They're helpful. You have that option. Another thing you can do too is if you are looking for practice, I included my old paper homeworks that are here as well. So I have like the blank homework and then the key to it as well. So if you want to like actually try like a paper based one that isn't my up in math, you don't have to deal with the I don't know anxiety of red checks or green checks or however you or sig figs then and you just want to kind of do old school paper homework like how the test is. The worksheets are there. They probably are a little hard, I think, compared to the videos and the probably the difficulty of the test, but it's more practice problems. It's getting exposed to more things. That's really the idea. You could spend time and go back through videos and rewatch them if you want. Thing with that, I think it's more important though that you probably do problems. If you are going to rewatch videos, probably the ones to consider watching are more like are probably the ones that are like the practice videos more than anything, like the longer ones that kind of take everything and combine them together. They're always a little bit harder, but it's because it's combining 7 concepts together into one video. And those ones are kind of more to help you guys. Um, the idea was to help link concepts beyond when I kind of design them in mine. Um, and really, we never get that much time in person to be able to kind of do that much stuff. So that's why, there is that video component to sort of help everybody see all those little details. So I would say make sure you're okay with your conversions, whether it's doing the formulas, pressure conversions, how to do Kelvin, right? Celsius to Kelvin, how to go from atmosphere to torr to millimeters of mercury, all that kind of stuff. I think are really important. And maybe the basics of how gases work, right? Being that we did talk about kinetic molecular theory, right? That's how we describe a gas. It's like a billiard ball that doesn't interact with anything. Make sure you're okay with kind of describing it. Are there any kind of questions about the gases or any of that stuff so far? I had to make coffee before this, that way I stay energetic. Okay. Well, in the meantime, after that, I would say with the aqueous stuff, there's probably not. There is some chapter 9 problems on there, but it's I try to shy away from making any crazy concentration problems. You will have to do a molarity problem. You will have to do a dilution problem. I don't think there's anything with molality because I think it's the devil. I don't think there's anything with percents on there that I can think of. I don't think I did. Now I'm gonna realize there's gonna be one on there, and I'll be like, like $8 that wouldn't be on there. And I likes molality. Oh, molality is like I don't know. I think it's made up. No, it's real. It's a real unit. It's just I don't know. I don't see the purpose of it anymore. So molarity's on there. You will have to make sure you know when to use the dilution formula or when to use molarity as a conversion factor, right? Molarity is when we use that one more for solution concentrations and then for doing unit conversions in a chemical equation. The dilution formula, this is where a lot of people make a mistake, is only for when you're making something less concentrated. So look for the keyword diluting when you're using that C1 V1 is equal to C2 V2 equation. That's only for diluting. Stoichiometry uses molarity or molality. It could use molality too, but we never did that in class. So you guys are okay there. In terms of properties, I would say make sure you're okay with understanding the definitions between aqueous reactions. That's probably one of the areas I kind of find to be more important just because many of you are studying biology. The biological body, or the body as a whole, is made of 70% water. So you have to be able to understand the relationship between water and solute, solvent, solute relationships, and how we can describe a solute, a solvent, a solution, and how that kind of works within the body, and understand the basics of whether it's colligative properties or know the basics of intermolecular forces that kind of tie into it as well, like knowing a water hydrogen bonds, like how can you see a hydrogen bond and how that interaction entirely works. Um, and being that it is such a heavily used part of physiology, especially when you start learning about cells and the blood system and how red blood cells work or how the cell membranes work and all these different things with diffusion and osmosis. And a lot of you probably, if you're taking anatomy now, you might already, especially if you're taking A and P1, you might already been exposed to a lot of these things because in class, a lot of people are familiar with hydrophilic and hydrophobic. So you already kind of know. So you need to make sure you're okay with those basics with chapter 9. After that, stoichiometry. Oh, I forgot I didn't. Actually, maybe that's still okay. Okay, I ignore the part that says minor part. I forgot to kind of edit this from the last time I gave this exam from summer. I thought I edited it. I guess it didn't save it. The only part of stoichiometry that I put on there is I put mass to mass stoichiometry. I did mole stuff, so anything with mole stoichiometry. I don't think, if I recall correctly, I don't think I did any gas law stoichiometry or solution stoichiometry. Just speaking that it's something that usually never is on the final when it comes to the standardized test. And to be quite honest, it is very, very hard, right? And you guys are seeing that from lab and also from class. So I think if you can kind of understand it in those respects when it comes to lab, I think that's okay. I think that's good enough for now. But just keep in mind for anyone, for those of you, because I'm thinking of a few of you who are in here right now who are doing Chem 1A, we will need it for Chem 1A. So make sure you're good with your stoichiometry for later, because I know at least 3 people in this call are going to be my Chem 1A class. Or in one of the Chem 1A sections. So make sure you're okay with doing your stoichiometry, because it gets kind of taught really early on in that class. So we're only going to do mass to mass stoichiometry and the mole to mole, I'm pretty sure. But it doesn't hurt to kind of put it on your flashcard anyway, just in case I'm misremembering, being that I'd made our test, my other classes test, and the resume review. So now I'm like, which one is which? My brain, all within the past like 3 days, 4 days. So I'm trying to make sure I don't get them all mixed up, and also, other stuff. Yeah, stoichiometry is my favorite. I don't know if it sounds sarcastic, but usually, I don't know. A few of you have told me stoichiometry is like your actual favorite, and I'm like, I hear that like every semester where some people say stoichiometry is their favorite, and I'm like, man, I must be doing a pretty okay job at like trying to lead you guys up to it. It's really not that bad after once you kind of realize that it really is chemical reactions and unit conversions. It's really all we've done before. It's not anything new. Even the mole to mole relationship isn't new. That's from chapter 5. It's just now we're using it to a chemical reaction. Anything with mole conversions is my friend? Oh no. No, I'm not sure anymore. So I do have a lot of recommended problems for all those chapters. I would make sure you're okay with doing them. You know that they're going to be the ones towards the back of the test, just because you got to show your work for them. Biggest thing, right? You got to write your units for them more than anything. Please do that. It will just be a disaster if you don't. You don't want that. Please write your units. Hmm. All right. Anything else that's on here? I don't think so. All right. Let's go back to that module. I do have the practice exam here. I'll add, so these Kahoots that are here are old ones. It's not the one we're doing tonight. And I do post the recording, and I do edit out all like the quiet sections, any of the timers. Do the Kahoot on your own, and then like, whenever you're stuck in a problem, I put all the chapter markers in the video. So on YouTube, so that way you can fast forward right to the question you get wrong. So let's say if you get first 7 of them you get right, and you're like, oh, I'm doing great, and then all of a sudden you get number 8 wrong, you can fast forward right to that specific question and see like maybe whatever I do to explain it and help you, versus watching a whole 2-hour recording. You could watch the whole thing if you want on like 2 times speed, being I see some of you watching some of my videos on 2 times speed. I'm like, I know I speak slow, but I don't speak that slow. I see how it is, but you can kind of fast forward and jump around. All right, so the first question. All right, we are back to that. All right, back normal. All right, this one, I try to put some theory questions on there, being that there are a couple multiple choice that are talking about the basic ideas of theory behind the chemical expression. So with this one, when it comes to a gas, if you remember, a gas does not have a definite size, and it does not have a definite shape, which means that it takes the size of whatever it's in. So, for example, if I take all the oxygen that's around you, right, it's the size of the room that you're currently in. But if you take it all and you compress it and put it in a gas cylinder, let's say, and you wanted to breathe out of the gas cylinder, well, you could do that, right? So you can compress it to one location. It's because the gas is really far apart. And the reason you can compress it is because it does not really have that strong of interactions. So they're not really attracted to each other. They're not really repelling each other. And it's because they're mainly nonpolar molecules for the most part. So that's why it is the green one. So we like to assume that it has no intermolecular forces. Okay, if the atmospheric pressure in Colorado is 0.8800 atmospheres, what is the pressure expressed in millimeters of mercury? And like I said, you do have the yellow sheet for this one. So while you're kind of going through this review, you're welcome to use your notes if you want to help you kind of figure out where things are and to kind of do things. But if you want to try to push yourselves, only use the yellow and the solubility sheet, and maybe even you have your note card if you're really ambitious, then you could try doing that, or maybe write things down if you're like, ooh, I'm gonna put that on my note card. It's always a good idea. Looks like pretty much almost everybody got this one, so which is good. So just a kind of quick little review of how this one works. So we're using that millimeter mercury to ATM conversion. Most of you probably realize that it's using that 760 millimeters of mercury as an atmosphere. So if you were to kind of to go through this one, just kind of, if we were just to kind of see this on our how to kind of do this one, it's simply taking, oh, that's really big, is taking our pressure. So it's 8800 atmosphere. And then we're just converting it with our conversion factor. So we set up our little T table, and it's 1 atmosphere is 760 millimeters of mercury. Just kind of as a little reminder too, that's also equivalent to torr, in case maybe you had to do a torr conversion or something. So when we just times those two together, right? So 0.8800 times 760, you would get about 668.8 millimeters of mercury. That would be your answer. Okay. Not too bad, hopefully. Okay, let's go back to our next question. And if at any point anyone has any questions, feel free to ask. You know, it's your guys' review as much as it's mine. You know, I'm just trying to come up with questions. So ask anything you want. A sample of gas occupies 24.5 liters at a pressure of 1.57 atmospheres. What is the pressure if the volume is increased to 48.3 liters? All right, so for this particular question, with question number 3, what we're going to be looking at is we're going to be looking at the combined gas law in order to solve this one. So the first thing that you always want to do with these kind of problems is you want to write down all the different values that are here. Now, whether or not you realize you had to use the combined gas law or Boyle's law, they both would be the correct answer. The biggest thing is I like using the combined gas law because it can be used for about 4 or 5 different types of problems. The biggest thing that's the most important is recognizing what is constant, meaning what is not changing. So in this problem, you'll kind of see that temperature moles are not even mentioned in the problem, meaning that they are what is considered to be held constant. They are not changing. So our formula can evolve into P1 V1 is equal to P2 V2. So being that we are trying to solve for the new pressure, final pressure, we have to rearrange our equation, meaning we have to get the pressure by itself. So in order to do that, we need to divide the volume by both sides in order to cancel it out and get the pressure by itself. So when we do that, we get P1 V1 divided by V2 is equal to P2. And now what we're going to do is we're going to now plug in all of our values into this expression. So we have 1.57 atmospheres times 24.5 liters. And that's going to be divided by 48.3 liters. So when we solve for that, we do 1.57 times 24.5 divided by 48.3. And what we should get for our answer when we do that entire expression is we will get 0.796 atmospheres for our answer. Now, one of the things to point out with this one is you can do some little predictions for yourself as well. So it's in order to help eliminate answers. So if you notice that when you go from V1 to V2, the volume is increasing. So what happens with that? Well, whenever volume increases, the pressure ends up decreasing. So if you notice, the pressure is smaller than the number you started with in the problem. In the multiple choice answers, you can eliminate about 2 or 3 choices by just knowing that simple fact without doing any math. So let's say if you were short on time, you only had a few minutes left of your test, and you're like, oh crap, I got this gas law problem to do. If you can recognize that, it can save you time, it can save you points, and it can get you a better grade, right? So let's go to our next problem. What volume will be occupied by 4 grams of oxygen at STP? Well, there's 2 ways to think about it. You can use the ideal gas law. You could do that. That's the longer way. It is a diatomic. So being that that is a diatomic, you do got to consider that in terms of the molar mass, right? So it's times 2. So it's 15.999 times 2. Yeah, a lot of people forget that one, right? Those diatomics, it's probably one of the biggest mistakes. Oh my God. How many, how many times I made that mistake when I was in general chemistry? It's one of the reasons why I tell you guys it all the time, because I did it too. Everybody does it. It's the way that they exist. It's the way we got to remember it. So when it's at STP, the first thing, right, your goal with any type of stoichiometry, gas law, is usually to get the moles, especially if you're going from grams to moles, if you want to use it in an ideal gas law or whatever formula. So if we were to set this up, right, if I have 4 grams of O2, I need to use the molar mass to convert it, right? So it's not going to be 16 grams, but it's going to be closer to 32. And this is for O2. Now, when we do that, you have a choice. You can either stop here and put it in the ideal gas law, because STP, right, that's the standard temperature and pressure. So that means it's at 273 Kelvin, and then it's also at 1 atmosphere as well. So you can do that. But there's an easier way, which is when it's at STP, you can use the molar volume as a conversion. Then this is only for STP, which is when 1 mole of gas is 22.4 liters. So if you kind of remember that one, I'll just write diatomics in huge font on my note card. Yeah, go ahead. You can do that. So if you do 4 divided by 32 times 22.4, you'll get roughly about 2.80 liters as your final answer. Okay. You can plug it into the ideal gas law too. So if you have the mole value and plug it into PV divided by RT, you could also, or not PV divided by RT, nRT divided by P. You could solve it that way as well, if you wanted to. That's another option. I personally recommend remembering the molar volume. It makes it a lot faster. All right, double points based on the following. The gas evolved I guess I made a typo there. The gas evolved from a chemical reaction is collected at 37.5 degrees C and 1.024 atmospheres. After purification, its volume was found to be 37 liters. How many moles of gas were collected? And you have your R constant, which is equal to 0.08206. All right, so this problem is an ideal gas law problem. So if you're ever given R in a problem, it's usually it's never not the ideal gas law. It tends to be a big clue for you just to so you can kind of recognize it. The hardest part usually about the ideal gas law, other than plugging in everything, is probably 1, making sure you're rearranging it correctly, right? So dusting off the algebra skills. Second one is making sure all your units are correct. So the big thing is that R constant, it has the units behind it, right? It's liters, atmosphere, mole, Kelvin. So everything needs to match here, right? So we have liters, that matches, atmosphere matches, moles is what we're trying to find, but you'll kind of see that the Kelvin part does not match the Celsius part. it needs to be in Kelvin, right? So the very first thing we want to do is we want to convert that to Kelvin. So if we do that, right, it's 37.5 plus that 273.15. Oh, that's why she put 0.15 in chat. 310.65 Kelvin would be the temperature there. And now what we're going to do is we're going to end up plugging in all those different pieces into the formula. So we're going to take that, we're going to rearrange our ideal gas law. So we're solving for N. So when we do that, we're dividing RT by both sides. So it's going to end up being PV divided by RT is equal to N. Now it's going to be 1.024 atmospheres multiplied by our volume. And then all of that is going to be divided by our R value times our temperature. Okay. So once we plug all those values into our calculator, right, what we should be getting afterwards, let's do 1 times 37, it equal, and divide by 8.808206 times 310.65. We should get about 1.49 moles of our gas that is being released in a reaction. You think your calculators are... I mean, maybe I could always double check. I didn't actually plug it in. I kind of just went off what's on Kahoot. I mean, I did it yesterday, but maybe I could have made a mistake yesterday. Let's double check. I got the same thing. So yeah, 1.49 moles. So it should be our answer. If your calculator had a stroke, then probably the biggest thing what you might have happened is parentheses, right? So when you're kind of plugging these guys in, make sure you put like the top and bottom in parentheses if you're doing it all in one big operation. You can also use the fraction button on your calculators. If you're using a TI-36, you have a fraction button. I don't think I have one on the 83. At least, I don't know. I've had this calculator since ever. I don't think I've ever seen one on here. But a lot of the calculators do have a fraction button, so you can avoid that. Ran out of time panic. Yeah, I mean, I just set a timer to it. So keep in mind, like if this is a test, if this was a math one, if you need a few extra minutes on it, then if you had all your numbers right and you were figuring out, then that's the most important part. Obviously, we want to get points. All about the points. It's about the Kahoot. That's what it's about. All right. Let's go to our next one. Okay, double points. More gas laws. Everybody's favorite. All right, let's take a look at if we have a mixture of the gases. We have oxygen, nitrogen, and argon have a total pressure of 800 millimeters of mercury. If the partial pressure of nitrogen is 80 millimeters of mercury and argon is 320 millimeters of mercury, what is the partial pressure of O2? All right, so way to set this up is you're using the law of partial pressure, so Dalton's law. And what Dalton's law teaches us is that if you have individual gases, the pressure of each individual gas added together is your total pressure. So for example, the total pressure that you feel in your room isn't anxiety. It is the pressure of oxygen, nitrogen, CO2, and all those other gases that are all around you that are kind of bearing down on us at all times. So with this one, it's all about addition and subtraction. So we have our total, which is 800 millimeters of mercury. We have our pressure of oxygen, and then we have our pressure of nitrogen, which is 80 millimeters of mercury. And then argon is 320 millimeters of mercury. So what we're doing is we got to kind of rearrange it. We got to do subtraction, some addition, subtraction. So being that we need to get PO2 by itself, what we're going to end up doing is adding the pressures on the right, so that makes 400. And then we need to subtract them from the right-hand side to get PO2 by itself. So when I do that, we have 800 minus 400. Right-hand side cancels, and then we're left with only 400 millimeters of mercury is equal to the pressure of O2. Okay, so that is how you do that. It's just a little bit of adding, subtracting. right? Keep in mind, if you need to cancel anything out, it's the opposite operation, right? With our good old algebra. Can't go wrong there. All right. What is considered to be the major portion of a solution? We were all over the place on this one, surprisingly. Oh boy. Okay. The solute is the minor component. That's a small piece of it. Like, for example, when we made our solutions in lab, when you had those little volumetric flasks, you added salt. Salt was your solute. Water, which is doing the dissolving, is your solvent. Okay, so that's the major component is the solvent. The solution is the total, all of it together. So solute, solvent is solution. Aqueous, all that is for the person to pick that is referring to when something is dissolved. So it's whenever you have something that is going through that dissolution, it's being ionized in the solution. Being less stupid as we go. Good. And did anyone, what was blue, red? Okay, so people just pick solute and solvent mainly. I was like, good, no one picked gas. Well, solute is a liquid. I mean, it can be a liquid. It's not wrong, but it's wrong in this case. But it is a term for solutions. But solute is the minor component. Based on the solubility rules, which one of these compounds is insoluble in water? So you got to take out your green sheet for these. You got to figure out what's insoluble. You better not just guess. This is hopefully an easy question because you have the reference. It's bring back the elementary school vibes. It's like, no, it's actually the college vibes, I think. We're going backwards. I don't know. I always kind of feel so conflicted the fact that I use Kahoots for my classes. I'm like, God, I feel like my students are going to think that I'm treating them like kids. I'm like, I think it's fun. I think it makes it more fun. Okay, looks like everybody got this one, which is good, but let's still kind of talk about it, just at least for the recording's sake. So good job figuring this one out. Big thing is, so I think I have the old version of the green sheet. I couldn't find the current one, so I think yours looks slightly different than the old one, slightly. The big thing, what you would do with a problem like this is you got to look up each of the answers, and you got to break it down into what their two ions are. So if you go through it, the first one is silver and bromine is what that first one would break down into, right? So it would be Ag plus and Br minus. So you're looking for those two components, and you'll see that we have a bromine, right? So this is one of them. And being that it's our first choice, it's a little bit easier. So you see that, okay, well, bromine is soluble, except when it's bound to silver. All right, so that tells you that it's insoluble. So this would be a solid. The other ones, like, just kind of, just show how to use it if we had to. So the last one is sodium acetate. So if you had to do an acetate, that's a C2H3O2. So it looks like this is what the molecule was. So you see that one's always soluble no matter what. So you're just looking for like each individual ion is kind of the idea. It hopefully by this point doing those isn't too bad. Hope you've been through worse, especially if you got through experiment 10, then you're already an all-star. So good job. Okay, which process defines how ionic compounds break apart into constituent ions upon dissolution? Let's use science terms. We just talked about this. So what is the actual term for what this is called? Okay, good. Okay, good thing. Most of you guys got this one, which is great. So it maybe was a guess. If it was, then it's a good guess. I don't know. But what's happening, right? When something is being dissolved, it's dissociating, right? So that means it's breaking apart into its two ions. So it's dissociated, and then afterwards, it's then ionized afterwards. But dissociation is the first part. Division is not a bad guess because it is, you are taking into two pieces. But dissociation is the correct term for that one. Being that, probably out of all those choices, dissociation, decomposition are right, the two chemical terms you've seen before. It was one or the other, right? So dissociation is referring to this one, being that they are just breaking apart. They're not reacting or turning into anything new. It's just it's still its original components. Decomposition would be if a reaction happens. Division, we'll keep that to the math people. They can use that term. Multi-select, double points. Which of the following compounds would form hydrogen bonds in water? So this one, how do you remember if it hydrogen bonds? Is that remember F no to hydrogen bonds? So F that. So meaning that you're looking for fluorine, nitrogen, or oxygen are the different species you're looking for. So whenever you're kind of looking at these different formulas, you're looking for nitrogen attached to hydrogen. So you see red, or an alcohol group is OH bonded to a hydrogen, or you see another O bonded to a hydrogen here. These other ones have the hydrogens are attached to the carbon components. Okay. Is that green one even real? Yeah, no, that's real. That one is 1, 2. How many carbons is that? 3, 4, 5, 6, 7, 8, 9. So that's nonane is the name of that chemical. So non meaning 9. It's one more carbon than octane, right? So octane is what powers your car, right? For gas. Good grief. Dang it, the orange one got me. Orange one's a good guess. So that one, it does look like it's bonded that way. But the way that structure looks like, the O is like in the middle, and then it has like two kind of carbons kind of coming off of it. So it's like holding hands, which each of the carbons on both sides. So I always like to kind of consider that one like where the oxygen's like the kid and it's being like swung by its two parents on the two sides. That's the way I picture those ones. Those are known as ethers. Is what that kind of chemical is. Which one of these has the highest boiling point? So with this guy, I realized I didn't really talk about this in class, so I did talk about it in a video though. It's a lot easier than you might realize. It's all about how many ions can it break down into. So if the more ions it can break down into when it is dissolved, then it will have a higher boiling point or a lower freezing point. So it's all based on how it dissolves. If it breaks down into like 4 ions, that's going to have a higher boiling point than something with like 3, and something higher than something with 2, and something higher than something with 1. So we'll look at that. We'll look at the answer. So the first one was this one. So if we were talking about dissolving, it's all about how many ions can it break down into. So we look at our cation, right? We have aluminum 3 plus, and we would have 3 nitrate ions. So the way I like to think about these is if you take the molecule and then you shatter it, right? Like it's a piece of glass. How many pieces can it break into? So when you're looking at the math here, you're just adding the coefficients. So we have 1 plus 3. That means we have 4. So we're just comparing that number with each one. So like if I look at the next one, right, Na2SO4, well, how many pieces do I have for this one? Well, I have 2 sodiums and then 1 sulfate. So what would that end up being? This would be 2 plus 1 is equal to 3. So far, this one is the highest. Now, when you're comparing other ones, well, oh my God. Yeah, we need the bunny as the morale boost. Oh my God, that bunny is so freaking cute. Comparing to other solutions, the lowest one is always going to be pure water because it doesn't dissociate into anything other than water. After that, the other ones that don't dissolve, so they dissolve, but they don't break down. So like sugar, for example, sugar will dissolve, but it doesn't ionize. So it just turns into an aqueous solution. So this is what we call a non-electrolyte. So this one would be just equal to 1. So you're comparing like that number for each one. So whatever's the highest number. So the first one that we did was 4. That one would be the most ions out of all of them. So that's what you're just comparing. It's not terrible, but it's not unless you know the trick. So what this thing is called, these numbers here, these are called ionization factors. So if you ever seen that word on a homework before, it's called an ionization factor, meaning like how much of it's ionized. the bigger that ionization factor, usually the better it is at conducting electricity in terms of solution. So that's kind of the whole idea. I think Alize just needs to post more of pictures of her bunny in the Discord pets channel, because the only one that has really done anything is Jackie in that channel with her cat, and that was adorable. But I think more bunnies and more animals in that channel would be great. Calcium bromide is used in lithography, and photography. So, what is the molality of a solution prepared by dissolving 45.38 grams of cadmium bromide in 375 grams of water? Molality, right? It's moles of solute over kilograms of solvent. So the solute in this case is cadmium bromide. So the first thing that we need to do is we need to look up the molar mass of cadmium bromide. Does anyone did any of you actually happen to calculate it? Because I did not. We could do it though. 272.21 sounds reasonable. Did you end up getting the answer correct over there? Then you probably did. If 22, you didn't get it right. Uh-oh. All right, we'll see. 277.2 grams of cadmium bromide. So when we solve for this part, right, we're going to calculate how many moles we have. So we do 45.38 divided by 272.22. And what we should get is 0.1667 moles of our solute. And we're going to be dividing that by our solvent kilograms. So being that our solvent is 375, we need to convert that to kilograms. So we'll just divide that by 1,000. So that would be 0.375 kilograms. So when we divide 0.1667 divided by 0.375, we should get 0.444. How many sig figs do we have? 4 sig figs, 445. Molality, usually we use a cursive M to do that one. So, which I guess we must have rounded something a little off. So we got 446 as our answer. So, all right. So we have molality. So our next one, let's see, are we still in solutions or are we past solutions? Double points. More solutions. I think we have 1 or 2 more solutions. Potassium fluoride is used for frosting glass. Calculate the molarity of a solution prepared by dissolving 39.3 grams of potassium fluoride in enough water to produce 325 milliliters of solution. With this, right, we need our formula. We have molarity, which is moles over liters. So the first thing we were given is we have our mass of our KF. So what we have to do is we have to convert that to moles. So I already looked up I calculated the molar mass of potassium fluoride, right? So using our periodic table. So we'll convert this to moles. So it's going to be 58.098 grams KF. And then we'll just convert that real quick. So that'd be 39.3 divided by 58.098. So what we should get for that is 0.6764 moles of KF. And if you have more digits, even better. And then what we're going to do with that number is we're going to divide it by our liters of our solution. So we had 325 milliliters. So we would divide that by 0.325 liters. And then when we do that, we should get a molarity of 2.08 moles over liters, which is 2.08 big M. All right, what volume of a 3.25 molar solution of HCl is required to make 300 milliliter dilution with a concentration of 1.34 molar solution of HCl? So how would we make a dilution? All right. With this one, right, we have the following problem. So it says the big thing is we're going to be using dilution formula, but there's 2 things that are the hardest part. Is one, you need to make sure two of your units are canceling, so they have to match. So like in this case, the molarities are matching. right? So they'll cancel. If you have the volumes, they need to be the same unit. So when you're reading these problems carefully, it doesn't really matter if you get the ones and twos mixed up. What it does matter is if you got to make sure you get the pairs correct. So in this case, it says what volume of 3.25 molar. So that means that these two are paired together. Doesn't matter if you label it as 1 or 2, that volume, that concentration, they're together. So you don't know what volume of C1 or of that C you have, that concentration. Then it says, and you want to make 300 milliliters is what your goal is. So you have a vol flask that's 300 milliliters and you want to make this specific concentration. So what we're going to do is we got to rearrange our formula, plug it in. We're solving for V1. So it's going to be C2, V2 is all divided by C1 to get V1 by itself. So what we'll end up doing is we're going to end up kind of plugging it all in, right? Yeah, C1 V1 or M1 V1, they're the same formula. Yeah, so this is the same thing. You do M1 V1, this is M2 V2. They're the exact same formula. So when you plug it in, it's 1.34 molar times 300 mLs, all divided by 3.25 molar. And it should be a smaller volume because you're talking about the original solution. So you're taking from your stock bottle in this case. So when we do the math, we get roughly about 123.7 milliliters. We'll round that up to 3 sig figs. We have 124. Hopefully that matches my key. Okay, good. It does. Ooh. It does not have to be converted to liters. No, you do not have to. As long as if you're given a problem like this, if let's say if they're both milliliters, they have to both be milliliters or both be liters. It doesn't, as long as they cancel. It's kind of like the gas laws are the same way. The combined gas law, they don't have to be in liters if you do the combined gas law, as long as your units cancel. But if it's something where you're like, I just want to convert it every time for myself, so I'm consistent, I don't see a problem with that if you want to put in liters every time. I mean, if it makes you do it correctly every single time, do it until you're comfortable. In a balanced chemical equation, which statement best represents a balanced chemical equation? This one is it's really wordy. But really the whole idea is when you're looking at a chemical reaction, it has the same number of atoms of each type of atom on the left and the right side. So like if you have 10 carbons on the left, you have 10 carbons on the right, 6 oxygens on the left, 6 oxygens on the right. It's the number of atoms that you're looking for. Consider the balance equation shown and identify the statement that is not true. Now, this one was a little quick, so I apologize for that one. I should give you guys like an extra minute with these. So let's just kind of go through it together. So the first one said the coefficient of sodium sulfate is 1. So with this one, what makes it hard is if you're still not the most literate when it comes to chemical naming. That realistically, chemical naming comes to time. The longer you kind of speak the language, the better you'll get at it. It's true for any language, right? For a few, like for if any of you, I know a couple of you in class are learning, Spanish or American Sign Language, or maybe you learned English. Maybe maybe English is your second or your third language, and it just takes time. Same with chemistry, right? You'll get it down, whether you get it here or physio. You'll just take a few classes, and it'll become second nature. So sodium sulfate is this one, right? It's one on the left. So you can see it's a coefficient of 1, so that's true. Barium sulfite is produced in solid form. So barium sulfate is our product. We see it's solid, so that's true. Then it says 2NaCl also could be written as Na2Cl2. We never, ever, ever, ever do that. We don't carry out the two. Like in terms of counting atoms, sure, you could say there's 2 sodiums, 2 chlorines, but you don't actually physically carry out that operation mathematically. The 2 represents that you have 2 moles or 2 molecules of sodium chloride in the molecule. So that one's your answer. But this is to kind of go through the other ones. It says barium chloride is dissolved in water. So BaCl2, right? It's aqueous. So that's tell you, yep, that's true. And it says the products. Okay, so with this one, because I don't know how many of you guys are maybe not the best with that terminology, right? When we talk about the reaction yield arrow, the right side is the products. The left side is the reactants and what we're starting with. So the products are sodium chloride and barium sulfate, so that statement is also true. I like balancing makes sense to me. There is a little bit of the team assessment is all balancing. So if you're really good at balancing, then you're good to go. Have a good night, Alize. Thank you so much for being here. And you can always finish it on the recording and stuff like that. So have a good night. Thank you for sharing your bunny and showing us. Keep sending pictures. It makes my day whenever I see the bunny. All right, let's do our next one. So really like one, the purpose of that one is, oh, Peach. Is that the Peach is the name of the, okay, Peach is the name of the bunny. Damn, it should be Molecule. So that one kind of helps you with stoichiometry, because that's the whole idea. Stoichiometry is like trying to read a chemical equation. What does it mean? When the reaction shown is correctly balanced, coefficients are what? Sorry, there should be a D there. So how would you balance the following formula? So all these numbers are your coefficients. So balance it like normal, and then look at the answers. And I should have given you more than 60 seconds. I apologize for that. So, okay, let's see. So this one, okay, looks like everybody that was able to answer got it correct. If you're still working on it, no need to worry. It's, like I said, you got more time on the test, right? If you kind of think about it, you get about, 2-3 minutes per question on the test. So you get a little bit more time. And some of them are theory questions. So hopefully like you would know them right off the bat. So you get more time on others. The trick on this one is thinking about evening the odds. So if you kind of remember my list of tricks, I had in my videos for Saturday, and then had in class when we talked about balancing. One of the most common ones you'll hear me say a lot is, oh, you got to even the odds. So and usually that's referring to oxygen. Oxygen is notorious for having an odd number next to it. So we have 3 oxygens here. So what that means is we need to make it even, especially when we have an even number on the right side in the form of O2. So the first thing we can do is if we add a 2 in front of that, what we're going to see is that, all right, well, if I have 6 oxygens as a result of that, I'll put a 3 in front of O2, and then I'll put a 2 in front of KCl, and then it's going to be all balanced. So it's going to be a 2, 2, 3. It's going to be my coefficients. So sometimes starting on the oxygens and evening the odds can be the easiest way to kind of see it really quickly, especially when you see like the KCl is already balanced. You're like, oh, we're good to go. But the oxygens tend to be kind of a problem. This was one of the reactions you did. This was station 5 for lab 10. I believe that's station 5. The one that you guys burned with the Bunsen burners. When the reaction shown is correctly balanced, the coefficients are what? Balance it. There's one trick that I kind of mentioned to you guys. I don't know if I mentioned it in the videos for Saturday. I don't remember if I did or not. I do remember saying it for Monday, Wednesday, because I made sure I said it. With this one, when it's all pluses and minuses for the charges, does anyone remember if you need coefficients, if it's all plus ones and minus ones? It's already going to be balanced is your final product. So whenever it's all plus ones, minus ones, it's already balanced. So meaning you don't have to do anything for it. It's an amazing trick to know, because it could save you a lot of time of trying to checking everything. So it's whenever all the charges are plus 1, minus 1, it's already balanced. And this is the case for it's probably not the case all the time. I'm sure there's going to be one of you's going to find something where it doesn't work, but it works for double displacement for sure. Okay, so whenever you have that AB plus CD, it always works. So you'll see over here it's still plus minus. And then and you're like, wait, what about H2O? Well, if you write it as HOH, right, as for the balancing, it's still plus and minus. So it never changes charge. The only time that it can become an issue is if it's oxidation reduction, and then you gotta make sure, but that's not with double displacement. That is with a single and decomposition and combustion. The following reaction can be classified as what type or types of reaction can you say this is? The first one I was hoping you'd notice is a double displacement. So if you were able to kind of get to that, then you got almost the way. So double displacement would be like the acid base one in this case. So with it, right, we see it has a 3 plus minus plus 2 minus. So it's following A, B, C, D. So now with that, what can we go after that particular fact? Well, with this, you see that it has a H plus and then OH minus in the reaction. So we have a base and then an acid being added together. And you can see that it's making a salt and water. So that is our acid-base reaction. Now, precipitation is whenever we are making a solid. So one of the products, I believe at least I'm hoping, I'm not just guessing, but this says solid next to it. Yes, it does. So aluminum sulfate says solid next to it. So that tells you, hey, you have a chunk of something in your test tube. This is a solid that is forming. So when you write out the net ionic equation for it, it would reflect that solid in the liquid forming in this case, okay? So it's both. So it's both acid base and precipitation because you happen to make both. But yeah, know your classifications that way, because it asks a couple of them, at least 2 or 3 questions that are like, can you tell me what kind of reaction? In a typical oxidation reduction reaction, the electrons are transferred. I know Leo goes Gur. Well, that's the answer, is kind of how this is trying to explain Leo goes Gur. So with this one, just kind of think about it. So here we'll go to a tablet, and you guys should be able to see the question on your end too. So we're trying to think of Leo goes Gur. So how can we try to understand, how can we phrase that? So when we have a talented drawing, try my best. When we have a chemical, so let's say if we have A plus B. Well, one of them is going to be transferring a electron, right? So if we're thinking about we're too high with wording, Dr. Ann. I have lots of expectations. I believe in you guys. You guys are great. When we're talking about how things are transferred, the one on the left-hand side, this one is A is transferring to B. So is A losing an electron or is it gaining an electron? Let's start with that. What do you guys think? Is it going through oxidation or is it losing or gaining? Let's just do that. It's losing, right? Exactly. So being that this is losing one, that means that this one is going through oxidation. And then this guy over here is gaining one. So this is being reduced. So on the problem, it says the correct answer is, so it's saying the electrons are transferred. So that means it's being transferred from what is being oxidized. So on the left-hand side, this is oxidized. And it's being transferred to what is being reduced. Okay, so that's where that goes from. It kind of does mean the opposite of what you had think, right? So it's kind of it's losing, but it's giving it. It's doing it voluntarily. It's not that it wants to, but so it's going from one to the other. When it comes to knowing this, I don't. The thing is, I need to talk to the physio teachers how much you need to know oxidation reduction, because when you guys do the electron transport chain and you learn about the coenzymes of the body, so when you learn about NAD and FAD, which are your B vitamins, which assist in metabolism. It's all oxidation reduction reaction. So when you go through all that, I have a feeling you probably got to know at least the basics of it, at least when you kind of see it. Why would gaining be called reduction? I don't know. Maybe it's like reduction of number because it's becoming more negative. I don't know. I never actually thought about it before. What's negative is good when it comes to electrons. That's true. So I don't. Maybe because it's reducing the number because it's going like to the more negative side. So maybe that's considered a reduction. Oxidation, the reason why it's oxidized is usually anything with oxygen is typically what's losing the electrons. Usually, that's where that one comes from. I don't know. I never thought about it before. You gotta give me a question I never thought about before. I'll have to look into it, see if I can figure it out. Oxidation is positive, so the electrons are leaving the party. Oh my god. In which of the following is the oxidation number of oxygen equal to 0? For oxidation numbers, when something was equal to 0 was when it's found in its natural state. This is the way that I like to phrase it. Meaning it's found as like its metallic form. So if it's like a solid metal, or if it's found in its diatomic form is the other one. So in terms of diatomic oxygen, nitrogen, or any of those gases, the molecule as a whole has an oxidation number of 0, being that it is a covalent bond. So we would have it as that oxidation number is 0. In terms of H2O2, the oxygen does have a covalent number. It's still it's actually -1 in that example for oxygen. The net ionic reaction for the balanced chemical equation shown below is what? So this one you have 3 minutes. So see if you can figure out the balance or the net ionic equation. So this one actually does have a trick to it, but we'll go through the long way too. So the trick is, if you kind of notice, I already gave you the phases on it. Which means if you already have the phases, you don't have to go through the entire process of figuring out what's soluble and insoluble. So you can actually kind of cut to what the final answer is. And this is very common on the standardized test and also on even on sometimes my exams too, because I saw that the standardized test for the final does this, is it gave you all the phases. So what that means is when we get to our final answer, the net ionic equation, it has to show you creating something, meaning it's always going to show you making a solid, a liquid, or a gas, unless it's no reaction. So it's going to show you that or no reaction. It has to be one of those 4 things. So being that we have a solid, which is Ag2SO4, this thing is going to have to show you making that thing. So how would you make that? Well, that means you need 2 silver ions and a sulfate ion, which is your yellow answer. But if you were to do this right from top to bottom, how would you go through and show all the steps? If you didn't know that, you'd have to look up the solubility, right? So you'd look up each one of these chemicals, you determine if it's soluble or not. And then you would break down all the ions. So we'd have like 2 silvers, 2 nitrates, we'd have 2 potassiums, sulfate. Then we'd have the other side, which is 2 potassiums, 2 nitrates, and then our Ag2SO4, right? You never break apart solids, liquids, or gases. So then what we're going to do is we're going to look for everything that matches. So we'll see like the nitrates match. Then we got the potassiums match. So then the only things left are that reaction that I drew at the very bottom, right? Everything else is still what remains. So the things I highlighted are our spectator ions. right? So if you were asked a question like, what are the spectator ions? Well, that's going to be anything that you highlight. It's just what's watching. It's not what's actually doing the reaction. Or if you're asked like, what is created, then like what's to precipitate, for example, then this would be your answer. So like if we were to evaluate this question, or if it asks you like what gases evolved, then you could maybe ask that if it was a different type of reaction. So there's all kinds of things that you could be asked, in that kind of type of thing. If that makes sense. Spectator ions on the bench, right? Yeah, they're not actually doing anything. They're just on the bench the whole time. Okay. The combustion of propane gas is used to fuel barbecue grill. In order to produce 5.65 moles of water, how many moles of oxygen gas are needed? So when you do stoichiometry, there's really 4 major conversions that you're going to be doing more than anything. It's molar mass, right? Which is when we talk about usually about typically a solid, not always, but it's referring to a mass. Mole to mole, right? So when you're using the chemical equation, right, to describe going from one mole to another, molarity, which is moles to liters, and then the last one, which is aqueous, right? So anything that's liquid. And then PV is equal to nRT, which is a gas. That's moles to liters. Now this one, so to kind of bring up the prompt, it said we wanted to make 5.65 moles of water, and we want to know how many moles of oxygen there are. Well, all we have to do is a mole to mole conversion. So if we have mole of water, we want to convert 2 moles of O2. So what are we going to use to do that? Well, we're just going to read our chemical equation, right? So if I have 4 moles of water, that is equivalent to 5 moles of O2. So our moles will cancel of water. So all we do is 5.65 times 5 and then divided by 4. That's it. Not that bad. So when we do that, we should get 7.06 moles is our answer. Don't overthink a problem. Wow. It was like, it's not that bad, I promise. So make sure you're okay with doing the mole to mole conversion one. You don't want to get this one wrong because I'll give you, you guys are here and probably I don't know how many people watch the whole recording, but if this one you will have to do a mole to mole conversion, just a basic one like this. You don't want to overthink it. You want to get those easier points, right? Compared to the other stoichiometry ones. What mass of oxygen gas is required to react with calcium metal to produce 44.8 grams of calcium oxide? Let's talk about it. So with this problem, this one is very much a Chem 1A problem. Being that it has, meaning Chem 1A is for the majors level chemistry. It has a lot of unknowns about it, right? You have to do a lot of things. The first thing you got to do is you got to be able to figure out what the chemical equation, which alone can take a lot of time, to interpret and read it. Then you got to figure out the molar masses and then do the stoichiometry. So it's like a 3-step problem. And that's not even including how many math steps there are. So usually I give you a little bit more information if this was a test. This kind of problem could be on there, but I would give you more pieces, like whether I give you the molar mass or I would maybe give you the chemical equation or something to kind of speed you up on it. So with this one, the first one is predicting the chemical equation. So it said you had calcium reacting with oxygen gas. And it made calcium oxide. So calcium oxide is Ca and O next to each other. And then we have to balance it. So to balance it, you need a 2 to balance, remember, even the odds. So we want to even out the oxygens. And then we'll need a 2 in front of calcium. So we have that. Now the next part is whenever we need to figure out how many grams of oxygen we have, I figure out the molar masses for us already. So we're always going to start with the term that's by itself, which is our 44.8 grams of calcium oxide. what we're going to do is we're going to set up a stoichiometry expression using our t-table. So the first thing we need to do is cancel out grams. So in order to do that, we need to use the molar mass of calcium oxide, and that's equivalent to 1 mole of calcium oxide. All right. So when we do that, we see that our units cancel. Now, in order to do the mole to mole portion, this is where we use our chemical equation, right? So 2 moles of calcium oxide are equivalent to 1 mole of oxygen. So what we'll do is we'll write down that we have 2 moles CaO. That's equivalent to 1 mole O2. And then once we cancel out that portion, we then need to find our mass part, which would be the last part. So that's where we use the other molar mass that's here. So if I kind of move this over a little bit, make that a little tinier, we'll plug in our last molar mass. So 1 mole is equal to 31.998 grams of O2. Now that we have all of our pieces, right, those will cancel too. What we would do is we multiply everything on the top. So it'd be 44.8 times 31.998 grams. Then we would divide that by 56.079 times 2. And what we will get is 0.399 grams of O2 is needed for this reaction to happen. Okay. And that's kind of how, so this one is probably like, this is your standard, what we call the mass to mass stoichiometry, right? So this is kind of the one thing that you want to make sure you do know how to do is the mass to mass portion of it. Like I said, I would probably only have you do like pieces of this, whether if this was a question, maybe it might be like writing the reaction out or doing the stoichiometry. I don't throw them all in one problem. So don't kind of worry about like, oh, I didn't even know where to start. I didn't know how to predict it, like do all these other things. It would be one piece of it at a time. Being that, most of you guys, as I kind of tell many other faculty, you guys are brand new to, most of you are brand new to chemistry. Most of you never took chemistry before. So let's treat it like that, right? You're learning the basics. So one thing at a time, and then we combine it together into 1A. We have the following equation represents the formation of nitrogen dioxide. It's a major component of smog. If 0.68 moles of NO is reacted with 0.79 moles of O2 to produce NO2, limiting reactant is what? So this one, we have a limiting reactant problem. It's similar to the one that we did earlier, not the last problem, but the one before that. So what we need to do is we need to find the number of moles of NO2, but we need to do it with each starting reactant and figure out which one will run out first. So if we do, let's say, NO first, so we 0.68 moles of NO, we want to convert that to NO2. So 2 moles of NO is equivalent to 2 moles of NO2. And we'll see like, hey, this cancels. This part doesn't cancel. The 2's cancel. So it's going to be the same kind of number, right? So it's going to be 0.68 moles of NO2. The other one, right, we have 0.79 moles of O2, and we'll do the same conversion, right? So it's, in this case, it's 1 mole of O2 is equivalent to 2 moles of NO2. So we'll have 1 mole, we'll have 1 mole on the bottom. That's equivalent to 2 moles of NO2 on top. So we do 0.79 times 2. So it's going to be a bigger number, right? So that's going to be 1.58 moles. So which one is our limiting reactant? Well, it's always the one that's smaller, right? So the 0.68 moles is going to be the smaller amount that we can possibly make. So that means that our limiting reactant is NO, which would have been the blue answer, right? So that's the whole idea here, is whatever one is the smaller one. And this kind of problem you can do to mass as well, right? You can figure out which one makes a smaller mass. You can do it with volumes. There's all kinds of ways that you can make this problem harder if you wanted to. So eliminating reactant problem, there will be one on the test. There has to be one. Like you can't go through a chem class without doing one. As I kind of say, the titration is a rite of passage. Eliminating reactant problem is on there too. A reaction produces ammonia. The theoretical yield is 420 grams. What is the percent yield if the actual yield is 350 grams? It's always the actual divided by the theoretical times 100%. So the actual is what you are doing in lab, right? So that's what you find. The theoretical is your stoichiometry number. So if you're ever asked to find the theoretical yield, that means do stoichiometry is what that tells you, okay? So with this one, the actual yield was 350. We would divide that by 420. So 350 divided by 420 times 100, and what we would end up getting is 83.3% would be our answer. And that would be a very, very good yield to actually get for an experiment. Consider the reaction shown. You have N2 plus O2 makes 2NO. You have a delta H of 43.2 kilocals. When 50 grams of nitrogen reacts, how many kilocals will be created and is it released? Is it absorbed? How would you word how this is showing? So that has to do with if it's exo or endothermic. Okay, so with number 27, our last problem, how exactly do we go through solving this? So there's a couple things to point out. The first one is our enthalpy value, our delta H. In this case, if you notice that it's positive. So what that means is that the heat in this case is endothermic. Or whenever something is endothermic, that means it's being absorbed in the reaction. So in a reaction, heat is going to be a reactant in it. So that helps you eliminate essentially 3 out of 5 of the choices by knowing that alone, which is really, really nice. So when we're doing this, we always start with a term that's by itself, which is our grams, right? So what we're going to do is our goal is to convert this to moles. So we'll take our 50 grams of N2 and we're going to convert that to moles using our molar mass that was given to us in the problem. So we have 1 mole of NN2. And the way that we can end up using this term over here, this enthalpy term, is it is equivalent to the number of moles of each item in the chemical equation, right? So it's equivalent to the coefficient. So in this problem, there is 1 mole of nitrogen based on that coefficient. So 1 mole is equivalent to positive 43.1 or 0.2 kilocals. So what we'll do is we'll take 50, we'll multiply that by the 43.2, and then we're going to divide it by the 28.014. So when we do that, we're going to get a positive 77.1 kilocals as our answer. So it was absorbed, and we had 77.1 kilocals as our answer. Okay. Thank you so much for listening, and let's go to our conclusion. So I hope that this did end up helping so you understand kind of the basics here of really all the little pieces and bits of the different process. So good job, everybody, for participating. If you need help at all studying, you guys are welcome to send me emails. You can message me on Discord. You can... Hello, if you want, you can comment in the YouTube video description if you want. I end up answering on there too to people. There's all kinds of ways that you can try to get in touch with me, whatever makes it easier. If you want to, you can go through this again on your own, way after you kind of study a little bit. So this is what I use to make this one is an old test. So this will kind of it kind of gives you an idea. This is probably, say it's similar to the difficulty of ours, but there's a couple of questions that I pointed out that I think are a little bit harder than what you're going to get on this one. So like the ones I pointed out, the stoichiometry ones. But I hoped it helped. And thank you guys for listening. I appreciate it, as always. Well, thank you all so much for listening. If you made it to the end of this video, then thank you all for watching. I hope that this helped. If you have any questions, please comment below in the section below. If this is your first time here and you're part of my class or another class, please hit that like, hit that subscribe button. I appreciate all your support. You guys are wonderful as always. And I hope to see you all again later in the future. I'll see you all later. Bye now.